Welcome all. Let's just wait for 2 minutes. Yeah, let's see if someone joins. Otherwise, we'll start as we always do. Okay. So let's start. Let me switch on my camera. I'll also share my screen. Uh, just give me a second. Yep. Let me share my screen. Mm, mm, Great. Okay. That's fine. Uh, okay. So setup is all ready. We can start. Okay. So welcome all. Today is the sixth lecture, not the fifth lecture. So let me correct that. Actually, it's not a lecture, it's a session, live interaction session 6. We are halfway there into the course. Uh, so uh, by after today's class, we'll be halfway there. And today we're going to look at oblique shocks and expansion waves. I was expecting some audience today so that we could have had some good discussion, but that's also fine. Not everyone is not free at the time of the sessions, so that is fine. For the benefit of people who don't know me yet, are watching the series of these sessions for the first time, I am Shrey Sahai Gupta. I am the teaching assistant for this course, this NPTEL course. I am a doctoral student at ISC Bangalore in the Department of Mechanical Engineering. I did my bachelor's from IIT Ropar in 2020. Um Post that, I briefly worked in HPCL for around a year, and then came on to join my doctoral program in 2021 August. Um, yep, that's it. Here are my contact details. I have also shared the link to my website and LinkedIn. You can reach out to me if you have doubts outside of these sessions. Let's begin with the recap. So last time we did a recap of all the lectures. So let's do the lecture recap of last lecture, lecture 5. Uh, the first thing we did was to look at the entropy generation associated with a normal shock. And as we would see, so uh, see, total temperature across a normal shock remains a constant. Uh, if we talk in terms of total quantities, it we can directly see how entropy generation is directly related to total pressure loss. Okay, so we know that across a normal shock there is a drop in total pressure, which shall give rise to entropy rise. Why? Because if we look at TDS relations, we'll have something of this sort. Delta S is equals to minus R ln P naught uh, 2 divided by P naught 1. Now, this would imply that if P naught 2 by P naught 1 is less than 1, then minus R ln of this ratio, let's write this as total pressure ratio. Okay, or let me edit. Yeah, total pressure ratio. Then we know that if this is less than 1, then there is some entropy generation. But we know that there is an entropy change. But now we know that there has not been any mass transfer or heat transfer, which could cause any entropy change, which implies that there is only entropy generation that is going to happen. So this is something that we looked at in the last lecture. Let me just see what else we did last time. Okay. Yeah. So a couple of derivations, I guess. Then yeah, then we also looked at the weak limit. In the weak limit, we saw that delta S star had some interesting properties. We could see why shocks appear only in supersonic flow and subsonic flows. Uh, this would imply that the entropy change is negative, which is not possible because of the second law of thermodynamics. We did a small numerical. Uh, I guess we did a small numerical. That's it. Yep. So, and then we stopped. So, this is where we stopped. So, let's start today's content. Um, I was hoping for some discussion today. Wanted to see what all you guys have remember or still for have absorbed, and we could have picked up from there. But anyways, let's start. So we'll start with some numericals on theta beta relationships. Um, Relations. The first thing to do is just simply revise what all do we know about these relations. So let me do that as well. Let me open the. Just give me a second. If let me see if I'm recording everything. If everything is fine or not. Let me just see. I think I'm recording. I'm sharing as well. Perfect. Everything is fine. Uh, yep. Now, Yeah, this is there. Um, yep. So let me just jot down some relations. Okay. So what? Let's look at the geometry for a while of oblique shocks. What is going on? Basically, oblique shocks can be said to appear when the flow is deflected. Supersonic flow is deflected, uh, and uh, and that deflection will cause some compression, and that information. Sorry. So that information. Okay. Okay. So what will happen is what is wrong with this? Hmm. Now, okay, I'll also draw a angle to demarcate that there is like to just demarcate that the magnitude of that this deflection, whatever deflection is forced. So let me just do that as well. This deflection angle is called uh, theta, or at least we'll call it theta. What is wrong? Okay, let me draw these things in black so that you know what is going on. So this is theta. Okay, this is the angle by which the flow is deflected. This is the deflection angle. Okay, and so the flow is deflected by this angle. Okay, now what that means is the flow was initially parallel to this surface. Let's call this surface as AB, and later on we are forcing this flow to be parallel to surface BC. Uh, let's say BC, and that will require the flow to get deflected by angle theta. Now, what happens is that there is a shock that appears because of this. So I'll draw that too. There might be a shock. Now, this shock, let me draw it with some fancy color. Maybe yeah, this is okay. Okay, so there will be a shock. Let me just write that down here. So there is going to be an oblique shock. Okay. Now the control volume we will choose will be of this sorts. So it will be something very parallel to this surface. So let me just. Mhm. The only thing that I'm going to do is, yeah. So let's see what goes on here. Okay. Uh, Let me do this jotted thing, this dashed thing there, and yeah. So command D, something of maybe at an angle of this thing perpendicular, I guess. Check. Maybe let's say this is the angle with which you want to close the surface for time being. Okay. So this is the, if we want to analyze this thing, the control volume we will choose, we can choose it in this manner, and there will be a flow in this control volume, and there will be a flow at this end. Okay. So now there are two things. We are not going to do the entire derivation, but there are two things that we'll see. First of all, perpendicular to the shock, perpendicular to the oblique shock, we can treat it as a normal one, as a normal shock. Okay. Uh, the tangential velocity. Tangential velocity means the velocity in the direction, the velocity component in the direction of the oblique shock. Tangential velocity component is conserved across the shock. So these are two things that we'll see. One more important thing is that the shock angle is something that we will call as beta. So let me just write that down. Okay, now just one more thing. Okay, this is also black. Um, Anyways, so this is how if we start treating this surface, I not marked it. Let me just mark it also, so that we don't have any like, just for the completeness of everything. For the figure, if we mark it as A, then B, then C, D, and finally F. So we can do mass balance and momentum balance, and maybe not energy balance is not required. Uh, and we can get this these relations. So the relation that I'm going to write now, again, these are also very descriptive relations in the sense that they are only true for caloric of the gas. So just remember that. Okay. Anyways, if we are not concerned about that, and I don't get in this um, course, the problems that we get in this course are going to be centered around the theoretically perfect perfect test case. We can just go ahead and look at the problems, and that is what we're going to solve. The problems that we're going to solve are also going to be um, centered on this perfect guess. Okay, so let me just go to the formula. Let me see. It's taking a little bit time today. Yeah, everything is okay. Yes, so certain relations that we need to write down. So just try that. it says tan theta. This is something that you have to derive, but you don't need to per se. Cot beta. So 2 cot beta, then you have this relation m1 sine beta uh, whole raised to the power square, raised to the power 2, I mean, divide by um, m1. M1 is the upstream or the Mach number ahead of the oblique shock. Cos 2 beta plus 1 plus 2. So this is a relation that given beta and m, you can find theta, which is a little bit uh, implicit because the way we have introduced the problem, it appears that we would generally know theta and something beta is something that we want to know. But there can be possibilities where you can measure beta and theta is some small value or maybe where some large value which you don't can't measure, and then this formula is very convenient. But otherwise, this formula right now is in an implicit form and it is not very convenient. Um, Note how so this is one thing. The second thing is that normal to the way I wrote it down, perpendicular to the oblique shock, in the direction perpendicular to the oblique shock, we can start using the relations for normal shocks. Okay, so that also is something that I want to just write the formula for before going ahead. So let me do that as well. Okay, so the other relation, the normal shock, another normal shock relation that we're going to use today heavily is normal shock. Let me write that relation. This is an oblique shock relation, so let me write that as well. Okay, so with that, you have m2 square is equals to you have gamma minus 1 m1 square plus 2, and then you have 2 gamma m1 square plus 1 minus gamma. Okay, so this is the another relation that we're going to use today. Okay, the first let's do the first thing first. Okay, uh, okay. Did I do something? Okay, X. Just let me do coloring here. Okay, okay. Yes. So now let me share another screen for you guys to see what am I doing right now. Okay. So this is again. So there are two ways to deal with this. Okay. Now this implicit formula, there is when see you are gonna solve these problems using tables. But for the sake of this tutorial or this live session, I thought because we are doing this online, let me use an online tool, graphing tool that will just so that you can see what am I doing. See, tables do not give a graphical understanding. You don't understand what is going on. Uh, and even the first problem today is going to understand this tan theta beta relationship. What are the deep intricacies of this relation? Okay, so generally what you will see is that um, okay, I think this is okay. Okay. Just give me. So now you can see the screen at least. So we are going to focus only in this region because given this function, so what have I done? Let's look at first of all. I've implemented the same formula first of all. Uh, Gamma. So this G is the gamma value which I have kept here. Um, This is X stores the theta value, Y stores the beta value. And so X is theta, Y is beta. Just remember that. And now we'll see that the this whatever this very complicated implicit equation is gives something of this sort for different Mach numbers. So Mach number is a parameter to this relation. And what we will see is uh, that as we increase the Mach number, this nose increases. This is something which you can see in the books also. A couple of things that we will note here is that this function at theta equals to 9, theta equals to 0, beta is always 90. So first, let's note that down somewhere. Um, Maybe here itself. So a couple of properties of theta beta relationship. Let me just do that also. So the first thing that we note here is properties, properties. Theta, or let's say beta of theta equals to 0 is always 90 degrees. Wait, sorry. So that's not true. Actually, there are two solutions to it. So let me just point that out too. So at theta equals to 0, there are two solutions. Okay. There are two solutions at theta equals to 0. Beta can be either 90 or there is another solution. There is a strong solution. There's a strong solution and there's a weak solution. And we'll talk about both the solutions. Again, why we are calling strong solution or weak solution? Because we know that in one, the beta value is small and in other, beta value is always 90 degrees. Let me point that also. Okay. Or some value. Now, what is this value? First of all, let's find that value. So let's see. Uh, so we know one solution is 90. What is the other solution? And let's see that from the formula itself. So first let's calculate limit. Uh, I think you are not able to see this. So yeah, now you will find. So limit theta goes to 0. What is my beta value? Beta value. We have to find out. So let's try to substitute that in that expression. Okay, that's all we can do right now. Okay, so now we know that theta tending to 0 implies what does it imply? Let's see. It implies when does tan theta, what does tan theta, theta going to 0, what does it imply? Tan theta implies that this will go to 0. So this will approach 0. Okay. Now you see either the denominator can go to infinity. That is a possibility. But and I think I've written it incorrectly. Let me just check if I've written the formula correctly or not. There is some small mistake which I made. I'll correct that. So there is a square power that is there. So note that it's not m1. The Mach number has this square dependence. So you can have an explicit dependence on the square of Mach number rather than Mach number itself in both in the entirety of this formula. Coming back, someone has tried to join, but um, think yeah, it's good. Now, as you were saying, um, either one the denominator can go to infinity, which means the number will go to infinity, or which is again not a practical situation kind of thing. It does not make sense. Or we can simply have two scenarios. Either this term, the bracketed term goes to 0, which implies that sine beta is m1. M1 sine beta is 1. Okay. M1 sine beta is a real number. In fact, it is a positive number. And that implies the beta has to be sine inverse m. Okay, that is one solution. Another solution for beta is 0. Isn't it? Now, for beta goes to 0 and beta goes to infinity, which implies that theta is 90. So that is the other solution. So that is how we are getting. So either m1 sin beta goes to 1 or tan beta goes to infinity. So these are the only two ways. And tan beta going to infinity implies that beta will become 90 and or m1 sin beta becoming 1. Now, why am I calling this um, strong and weak solution? First of all, note that when theta is 0, which means that the flow is not getting deflected, but the oblique shock is perpendicular to the initial flow. What exactly is that? That is the normal shock solution. So if you're getting theta equals to 0, if you're getting a solution, this value of theta equals to 9, beta equals to 90 is directly giving you the normal shock relation, first of all. Second of all, now comes the uh, this concept of Mach waves. Suppose the theta is tending to 0. Theta is tending to 0 in both cases. But there is one normal shock, and then there is another one. Normal shock implies that the flow becomes subsonic downstream. But suppose theta is just 0. We do not expect for no reason, if there are no like subsonic conditions downstream of this deflection surface, if this theta approaches 0, we expect the flow to remain not deviate very largely. It is a very small, like it will deviate very infinitesimally small, by a very infinitesimally small quantity. Suppose on a flat plate there is a perturbation, there is some small uh, ridge is there, some disturbance is there, some perturbation is there. The flow is still not getting deflected largely. There is small disturbance was there. In that case, you get a very weak Mach wave, and weak wave, which which gives you which and this wave signifies the travel of or propagation of this present propagation of information containing the presence of this perturbation, the small perturbation or the some small disturbance in the flow, and that is called Mach waves. Okay, so that is the weak solution. So we will see what happens when theta beta is tending to sine inverse m. Okay, what we will see is m2 will also be roughly m1. That is what we will see. Uh, because again, think about it, perpendicular to the Mach wave, m1 will be tending to 1. So perpendicular to this Mach wave, the flow is sonic, and we know downstream of a normal shock, when upstream flow is sonic, is also a sonic conditions. Okay, so downstream, if suppose if we know Mach number normal to the shock is mn1, that is 1. We know mn2 is also 1. We know beta is sine inverse m. Uh, but the deflection angle is still 0, so flow is not getting deflected. So now M2 M2 is what? So now let's write Mn1 and Mn2 in terms of M1 and M2. So let's do that also. So there is Mn1, which is M1 sine beta. This is something that we have seen in the video lectures. And this is M2 sine beta minus theta. This is what we have seen. You see, in the limit theta tends to 0, m1 sine beta equals to m2 sine m1 and mn1 equals to mn2, and that will be 1. And that implies that m1 will also be close to m2. So this is a small very weak wave, not doing anything, not doing much, and is just propagating some small presence of some small disturbance that can appear. The flow is not getting deflected, but there is a small perturbation which is causing rise in this origin of this Mach wave. That's it. Okay, so now let's get back um to this slide. So we know that there are two solutions. One is always 90. The other solution, you'll see, moves with the Mach number. And if you note, it was moving like sine inverse of um, 1 by m, not m, sine inverse of 1 by m. So that is also important. I think I've not done that. So yeah, sine inverse of 1 by m. Now, sine inverse is a one-to-one monotonic function. As m increases, 1 by m decreases. Sine inverse will also decrease. As Mach number increases, beta value will decrease corresponding to this Mach wave. Okay. So you see, as Mach number m increasing, this value is decreasing. Okay. In the limit, I guess in the limit Mach number equals to 1, both the solutions are gonna converge to 90 only. Okay. Because sine inverse 1 is what? Pi by 2. Anyways, so this is the general trend. We see there is a nose there. There is this nose that exists and so on. Now let's numerically see the effects of theta on beta and so on. Okay, so now let's do some numericals for that sake. Okay, so let me collect the numericals for today. Uh, um, so what numericals do we have? I have used this book uh, for the numericals also. So let's go ahead and write this. Okay, now let me just first write the equation. This Let me first just write the questions and then we'll come back to the solution. Let me first write the equations we are going to the questions that we are going to solve. I have to write it on the okay. So let's write. So there is this first example. Uh, so it has several parts. A uniform supersonic stream with M1 with Mark 1, Mark number as 3, 1 atmosphere pressure, and temperature is 288 kelvins. What is 288 kelvins? I guess 28 degrees or something, 25 degrees Celsius or something. Okay. Encounters compression corner. So it's called a compression corner. Just the same geometry on the last page, last slide, which deflects the stream by an angle of 20 degrees. Calculate. Now, A, this is the first part. Calculate P2. So the static pressure behind the shock, the static temperature behind the shock, the Mach number behind the shock, the total conditions behind the shock. Okay. Now the second part is uh, if the deflection angle is increased to 30 degrees, repeat the exercise. Repeat the exercise. Specifically, um, calculate the pressure, the static pressure, and Mach number behind the wave and see if the deflection angle is 20 degrees, but this time Mach number, the incident Mach number is increased to 5. Calculate calculate the conditions behind the shock. We know that there is going to be a shock. Compare the results. Results. What else? Okay. Note if you can the non-linearity of the relation of the Finish. Okay. I think these are only the three parts. I'm just gonna continue this. Now we are going to solve this problem. Before that, let me just go and use the washroom before I come back. So I'll just take 2 minutes and I'm gonna come back. So let's continue. Now I think I'll stop sharing and bring this here and share the screen. Right. I think yeah, we're sharing. Fine. Okay. So now let's solve this problem. The first part of the problem is let's what is this mark number? Mark number is 3, and second thing is theta value is given to us 20 degrees. Okay. So now what we have to do is either we can use the table, but I'm gonna use uh, this graph which I showed to see what is this beta value corresponding to. You see that it's an explicit equation. One more thing that we have, I've shaded the other area and highlighted an important like some area of it because this function is continuous. You see, it is periodic in both theta and beta. So to avoid uh, uh, for real or repeated solutions, let us just look at this window. Okay. So now we know that we know theta value. So for a given x, we need to find what is the y. Okay, that's it. So now we know that x is 20 degrees. So with that, there are two solutions that we want to get. Let's try with the weak solution because weak solution is the generally preferred solution. Nature prefers weak solution. Only the detached solutions are the strong solutions. So if you have a compression shock attached to the compression corner, there's a then you're going to have so we see corresponding to theta of 20, we see that there's a beta of 37.6. Again, let's go back to so we find out. So beta is 37.6. Okay. Now what is our next step? So step one is finding beta. What is step two? What is step two? Step two is finding M2. Okay, how we are going to do that is m n1 is m1 sine beta, which is what? Let's check what is that value. So we have m is our yeah, m is 3, that is okay. Sine m sine 37 and 37.6. One more thing, I've done this pi by 180 multiplication to ensure that we can put values in degrees, but the function takes the values in radians. So to do that, I've done that. Otherwise, there is a setting also to actually degrees we can do, but let's avoid. Let's not do that. Um, so now we know that mn1 is 1.838304. Okay. Now what we are going to do is use the, so now we know this value. The next logical step is to use the ideal, the normal shock relations to find mn2. mn2 has to be subsonic. Note that. But M2 does not have to be subsonic. M2 can be will be. In fact, it will be supersonic. So as you will see, M2 sine beta minus theta is what? So we'll find it through normal shock relations. Okay. So we find this value. Let's see again, I have a graph for this. So again, it's the same thing. So in this one, um, this is how it looks. This is the relation for subsonic to supersonic. So this is M1, this is M2. Now, for our X value, we have 1.834304. So let's see what MN2 value we will get. Okay, so the value we get is 0.60985. 0.60985. Generally, I don't prefer using so many significant digits, but in this case, I've seen that you can make some mistakes unless, like, you can make some mistakes if you don't consider the required significant digits. So to be on the safe side, I'm taking a lot of significant digits. Sometimes you don't need them. So because anyways, you don't need so many significant digits. The calculations we do in numericals or by hand calculations. Now, correspondingly, M2 can be found out as using this relation. Uh, Maybe it makes more sense uh, to write it as this. So what do you find? Let's again, instead of using the calculator, let me just go ahead and use this thing. So now we have mn2 is 0.60985, and in the argument we have beta minus theta. Beta is 37, theta is 20, so 17.6. We calculate m2 to be 2.017. So this is your m2. Now, how do you get, we were supposed to calculate P2, but the way to do it is first you find out the Mach numbers. Now, once you found out the Mach numbers, we can use the same oblique, this normal shock relations to find out the static pressure. See, in the direction perpendicular to the oblique shock, we're going to use that relation because static conditions will not change with rotation of our coordinate system. So we are going to use this relation of P1 by P2 by P1 will be a function of Mn2, Mn1, sorry. Okay, so let's calculate that. I have that. Oh, you're not able to see. So now P2 by P1, we are, the point is we will calculate P2 by P1. Again, it will be calculated as a function of Mn1. Okay, not M1 or M2 or Mn2. It's Mn1 because we are going to use normal shock relations. Okay, unless you go by a more difficult route, it is better to go through this Mn1 route. Okay, now uh, I have this relation back here itself, normal shock relation. This is the, I think, so I have it here only. Yes, so this is the one, Mn1. Now Mn1 is 1.8304 and correspondingly Rp is 6.06. See, look at this. This is the pressure ratio. This is the temperature ratio. This is the ratio in the density. Let me do it as RT. Okay. So this one is the pressure ratio. So P2 by P1 is 6.02, which implies that P2 is what? P2 is 6.02 atmosphere. And again, similarly, T2 by T1 is also something that you can calculate from this relation. Again, function of so now you can't see the screen, so let me have. So the function of Mn1, um, what is that? What is that ratio? We'll see from here. RT you will get as 1.677. So 1.677, and correspondingly, your T2 will be T2 will be T2 will be 1.67 times of 288, which is what? Let's check from the calculator itself. 1.677 into 288 will get us 482, 482.98. 482 or maybe 483 kelvins. Okay, now this is the first part. This is part A. Yeah, we also have stagnation quantities. Now, how do you calculate stagnation quantities? Let's do that also. How do you calculate P naught 2? So the easy way to calculate P naught 2 is to, now that you know P2, and now you know P2 and M2, you can just simply use the isentropic relations rather than going any other way. This is the simplest way to do it. So now P2, P naught 2 by P2 as a function of M2, we'll calculate. Um, let me open that calculator again back. So this one has this relation. Now here I can put X, whatever I want to put M value. What is M2? M2 is 2.017. So correspondingly we'll get yeah. So we are going to get 1.8136. So this is 8 times of, so this is around 8.03. And then let me just also get the value of P naught 2 by T2. I know that you can't see the screen right now. So okay, GHI. of N2. What is that ratio? Let's just see that ratio. The ratio is 1.8136. Okay, so now come back. Let's come back. Okay, so if we do that, we will see that P naught 2 is um, 8 times of 6, 8.03 into 6. So around 48 atmosphere. And this total temperature is 1.8 times of 483, which is what? So let's just use that web page only so that you can also see the calculation. So I'm calculating 1.8 uh, 136 into 483 is 875 kelvins. 876 actually. 876 kelvin. Okay. Uh, just one thing which I'll do is check if I've gotten, if we've done it correctly or if I've made some mistake anywhere. Probably not, but let's just check. So, so beta value is 37.8 graphically, but we have used 37.6, which is okay, not a problem. MN1 is 1.839, which is also fine. This MN1 calculation is also okay. M2 is okay. P2 by P1. P2 is 3 point, hey, 1 second. That's a mistake I made, it seems. Okay, okay, let me just correct that. There is some mistake which I made with P2 and P1. So let's just go back and see what. So here, this one, P2 by P1, right? Normal shock, RP, MN1 is 1.8304, RP is 6 times. Thing is wrong. What is MN? I'm using this wrong one. No, this is the relation. It's not. This is the ratio, not this one. So this is 3.74. Let me correct that. So this is 3.74. Okay, let's and also the temperature also 1.55 times. So wrong values I took. That is why. That's why I wanted to check if I've taken wrong values. So 3.7. What was it? Temperature I remember 1.5 something, 1.557. 1.554, 3.74. So this will make it as 3.74. And here it is 288 times 144. 288 and 144 is around what? 288, 144 is 388. 330 something. Let's see what is this number. 1.554 times 330 288 447, not 337, 447. 447 and so now this is okay. Now 8, this calculation will also go for a toss as it seems. 0.03 times 3.74 is 30. I think this is okay. 30 atmosphere. And this one would be 1.8136 times 447.5, which is 811. Okay. Let me just check if these numbers are okay or not. So these are the new numbers. Let me check if the numbers are fine or not. So 30 is okay. 3.74 is also fine. 447 is also okay. M2 is fine. 20. This is also fine. T naught is 806. Yeah, all the values are close enough. Some beta value we have taken different. So some division is there, but anyways, that does not matter. So the values are fine. Now, the important thing is to okay, so let's do this B part first of all. Okay, so let's do the B part first. Similar, it's a repetitive exercise, but it is good to just practice. So now M1 remains to be 3, but theta has turned to be 30. So now beta value will change. So let's make that change there. So if this value changes, now let's go closer so that we are accurate enough. This value is, I think it's 52. So let's take a 52 value. Yeah. So this is 52. So we'll change this value. This value will be 52.0. Let's calculate this value next. So M sine 52 is 2.364. 2.364. Corresponding normal shock we will see now. Corresponding normal shock for 2.364. The value beats at 0.527. So 0.527, 7, and then M2. Again, M2 will be what? Now let's go back. So this one, M2, this is 0.527, and this one is 52 minus 30 is 22. So you get 1.4, 1.406, 1.407, 1.407. Okay, now now we'll find other values also. So first let me just, because we wanted static pressure, or let's calculate. So function of Fm1, Mn1. So this is, let's calculate that also, just one things. Okay. Uh, Here itself, if I put Mn1 is 2.364, 2.364. So the pressure ratio that I get is 6.35. Now I'm getting 6.35, 53, and temperature ratio I'm getting is 2. So I will have 6.35, 6.35 atmosphere. And now we know 288. So twice of 288 is what? 576, 576 kelvins. So now let me just check if these much are okay or not. These values are fine or not. Have we done any mistake or something? So beta value is 52. Mn1 is 2.364. P2 by P1 is 6.276. So this pressure ratio value is fine. Mn2 is 0.527 is also okay. M2 is 1.41. Great. So now let's yeah. So this these values are fine. Mm, okay. Now we will also calculate stagnation pressure. Also let's calculate. P2 we know. This value we have to know. So this value is M2 is 1.407. So we go back. Here we will go 1.407. 1.407, and this is 1 point, so this is 1.395. Okay, so temperature ratio is 1.395. Pressure ratio is what? Total to static pressure ratio is what? 1.396 is 3.214. 3.214. 3.214. 3 point, array, 3.214. Now, this implies that the total temperature I'm calculating using my mobile, 3.214 times 6.35 is 20 times. So this is 20 atmosphere, and temperature is 1.395 times 576 is 803.52. I'll prematurely look at this portion of the question. Uh, let's note the non-linearity in these relations. See, theta increased by 1.5 times. Did beta increase by 1.5 times? Let's see. What is 1.5 times of 37.6? It's 56.4, but beta remains to 52. So a little bit lesser. What happens to M2? M2 decreases, and it decreases uh, not for sure not by uh, 1.5 times. So M2 is also, well, uh, theta has increased, so pressure ratio we can see. Okay. Now, as I was saying, let's look at the pressure ratios. Pressure ratios were 3.74. They increased by 1.5 times. 2.74. 3.74. 1.5 times is 5.6. The pressure increased by 6.35 times. Similarly, we can look at pressure. So one thing is that the pressure ratios, static pressure ratios of heat are nonlinear, have nonlinear relationship with theta. Okay, so that is one thing. Let me stop here. Let me talk to this person who has joined. Let me ask him if he has any questions or anything, and then we'll continue. So, hi Chaitanya. Do you have any questions or anything? Do you want to discuss? No, he left. Okay, so he just left, which is also okay, not a problem. Now let's go to this uh, third part of this question. Um, okay, so third part of the question is theta will remain 20, but we'll increase the Mach number. So now we'll see if Mach number is there a linearity between a Mach number and other quantities. For one thing, we know that the explicit dependence of Mach number is squared, it's to the power of 2. So there is not going to be any linearity, and the relationship is going to be non-linear. Okay. So this third part is Mach number is 5. Let's go back to the graph. Mach number I'll put as 5, and let's see, theta I'll put as back as 20. Let's see what do we get as beta value. So the beta value we get is 29.77. Okay, 29 point, let me put it as 29.8. So this is 29.8. Okay, anyways, 29.8. Now let's calculate the 29.8. Let's calculate the MN1. MN1 comes out to be 2.484. So I'll write that. So MN1 comes out to be 2.84. 2.84. 2.484. Okay. Let's calculate MN2, corresponding MN2. So you see that there is a prescribed procedure you just have to follow in these equations. That's why the questions you're gonna get in when in assignments or anything, they will complicate it. They will mix it with Prandtl-Meyer expansion waves and reflection waves to increase the complexity there. Okay, so that is one thing. Uh, okay. Let's go and look at the normal shock relations. So we have Mn1 as 2.484. The corresponding value for Mn2 is 0.5145. 0.5145. Uh, Now we will calculate M2. So for that, we need to calculate this expression. Um, yes, 0.5145, and theta minus beta is, so 29 minus, so 9.8, that's it. And you get 3.02. So you get 3.02. So M2 is now 3.02. Let's calculate the uh, static pressure ratio. Static pressure ratio, if you want to calculate, we have Mn1 we need to put as 2.484, and then the ratio comes out to be 7.03. So I'll just jot down that there, 7.032. Temperature ratio also, let's just note down as 2.12. Okay, so correspondingly, the pressure will be 7.032. Temperature will be twice, 2.12. So not just twice, so 2.12 times 288, I think, is 610, 611 or 10.5. Static pressure ratio and temperature ratio is also something that we can calculate. So let's do that. Or let's avoid that. Let me just see. Uh, have we done this one correctly or not? Do the answers match or not? So pressure ratio is fine. Mn1 is 2.5, M2 is 2.95. This it's close enough. Um, okay. So couple of things now. This question is done. So couple of things. The effect on beta of increasing theta and increasing Mach number. You note that when theta was increased, beta increased. So when theta increases, beta increases. Why? Because we have been looking at um, a weaker shock solution. It's not a weak shock as such, but the weaker shock solution, theta increases with beta. But as I showed to you, uh, the Mach wave solution, sine inverse 1 by m solution goes down as Mach number increases. So for a constant theta, as you increase Mach number, beta decreases. So that is the first thing to note. So that is the first thing to note. Again, we can also note, see, Mn1 is associated with the strength of the shock. Okay, so what happens with the strength of the shock? If you increase theta, your strength shock increases. If you increase Mach number, again, strength shock increases. So you see, strength shock is related to the upstream Mach number or the incident Mach number. If that Mach number increases, your shock strength is going to increase. It is also dependent on beta. Higher the beta value, higher will be the shock strength. But when you increase Mach number, you see that beta decreases. But the increase in Mach number is generally it generally outweighs the decrease associated with the beta value. So generally, with increase in Mach number or increase in the deflection angle, you get stronger shocks. That is why the pressure ratios you see is higher. Temperature ratios are also higher. Okay. So it is a general rule that as theta increases, the shock wave becomes stronger and beta increases. And similarly, if M1 increases, the shock wave becomes stronger and beta decreases. So shock wave is shock waves increase. Again, then there is a non-linearity also. You don't see linear behaviors. That is also there. Okay. What else can we do now? Then I have another set of questions that we'll look at. Um, okay. So next we're going to do another question. Let me jot that question down for you. I need a diagram for it. So I'll okay. Let me move ahead. So this is the geometry. Now let me write the question. Here the arrangement shown in the figure, 15-degree half angle half diamond wedge airfoil is in a supersonic flow at zero angle of of attack, a pitot tube is inserted into the flow at the location shown in figure shown. Pressure measured by the pitot. The pitot tube is 2.596 atmosphere at point A. On the back face, the pressure is zero point 0.1 atmosphere. Calculate the free stream Mach number. And so this is the question that we are going to do now. Uh, One important thing is that this involves something that we did in the in one of the previous lectures. So let me open up lectures slides for four. For the session four, I think we had expressions for how if we have the static pressure below ahead of the shock and behind the shock we can measure the total pressure, we can find out the Mach numbers. Okay, so we know that the ratio also is quite high. So the ratio is around 25. So we know it's a supersonic flow. Uh, so what relations do we have? Okay, okay. So the way we are going to do it is P naught 4 is known and P3 is also known. Then and that is 25.96. And what is that value? So we will first see P naught 4 by P4 times uh, P4 by P3. Right now, you see P naught 4 by P4 is something is a function of M4. M4 itself is a function of um, M3 and P4 by P3 is a function of M3. So this is how we are going to calculate it. Um, Now, this we had done last time. I'll write the expression for everything. So what do we have there? Okay. So M4, then uh, we are pretty sure that M4 is a supersonic number and it's not a subsonic thing. So we also know M4 is M4 is this. So actually you can just simply substitute this value there, right? And again, we this also we have. This value also we have. This is basically 1 plus 2 gamma divided by gamma minus 1 m3 square minus 1. I think this is what exactly what we had written previously also. I have not written that down there. Let me just check. It's 1 plus this thing. Gamma plus 1. Let me just check it again. Hmm, yeah, so this is okay. Now we have to actually find this relation out. So now what I'll do is I'll open another graphical thing. We'll calculate it again. This. Oh, let me just write down what is it. G is 1.4. Okay. So now we're going to write it as 1, or let me put it as G divided by G minus 1. 1 plus G minus 1 divided by 2 times 1 plus G minus 1 by 2 x square. Uh, and then we also wanted to write 1 plus 2 by 2g by g plus 1 x square minus 1. Okay, now we wanted the value for 25.96. What mark number will we get? So we're going to get two values. The other value is 4.444. So we expect mark 3 to mark number at location 3 to be 4.45. Let me just check if that is the correct value we have got, first of all. Yeah, so we get mark 3 is 4.45. This is fine. Now we'll traverse backwards. From 3 to we will go 1. Okay. So we have found successfully mark 3 we have found. Now what we are going to do is use the expansion wave. So Prandtl wave expansion expressions. So that I've not written down for you, but let me write that down for you. The expression for it, right? So the expression for that is mm, so the expression for that is mu of M is SQRT gamma plus 1 plus 1. Then we have 10 inverse, and then this thing, entire thing. So this expression you can find out from the book or something. Um, and you will have, this is okay. This is M square. So now you see that Prandtl expressions are isentropic things, right? They are isentropic. So you don't have to worry about pressure drops or anything. These are just isentropic relations. Okay. Then you have minus 10 inverse SQRT M square minus 1. So I think you can't see the entire thing, but now you can. There's one more thing to actually resolve the Mach number at 2, and that is so deflection angle is theta is mu um, mu m2 minus mu m1. That's it. So we need to find these new values, and from that we can find m2. So this is the relation. Now that I had written down in this web page, so I'll go back and close this, I guess, or let's not close it. So I've written it down here like this. Um, so we have a Mach number of 4.45. What is the mu value for it? Something is wrong, right? It is wrong. Hmm. It's okay. It's okay. It's not wrong. Thing is fine. So 4.45. What is the value that you have? 71.27 degrees. Okay. So mu of M3 is 4.45 is 71 point, what was it? 0.274, 27 degrees. Okay. Now we know deflection angle we know is given us to be, um, I think it's 30, right? No, let me check. So it's basically 15. Yeah, it's 30. So theta is known to us to be 30 from the figure 15 plus 15. So mu of uh, M2 will be 71.27 minus 30, which is 41.27, uh, which implies that if we go back and calculate value for 41.27, what value do we get? We get a Mach number of 2.593. So M2 is 2.5935. Okay. Hmm. Uh, okay. Now we know that now this becomes a simple problem. Uh, we know M2, but we don't know beta. Beta we need to calculate. So again, this is but we know theta. Theta is something that we know. We know M2, but we don't know beta. So this one is now a little, uh, it requires trial and error now. Okay. I think, yeah, this is fine. So now M2 is known. Now we don't know MN2. We don't actually, beta is not known. So we have to guess some beta values and see how things evolve. Okay. That is how we have to see. Um, Anyways, so let's start guessing some beta values. Okay. So insert draw. We'll draw table now. Okay. Let's see. So let's guess some beta values. What do you expect beta value to be? Mark number 2 is 2.6. Let's guess a value of beta to be, let's say 50 degrees, or let's say 30 degrees. Okay. And then also guess 20 degrees. And the next guess we'll take based on these values. So now if beta is this, theta is known to us, is known to us 20, 15 and 15, right? So from that, mn2 will be what? Mn2 will be what? Mn2 will be m2 sine of uh, 15 degrees, and that will be m2 sine of 5 degrees, right? So let's just calculate there. So we know mn2, m2, m is here, m is 2.56 we can take, and 2.6 sine of 15 degrees is how much? Is points is 0.673, or it can be, the next guess we have taken is this, so 0.22, 226. Now if we do that, then we have to find mn1 for these corresponding two values. So see, we have to find now mn2, mn1. So now we have to find mn1. I'll go to this one. Okay, and now I'll use y values. Okay, so y value is 0.673. You get m and 1 to be 1.585, and in this case, if this is 0.2, then so we see that it is a pretty low value. So 0.2 maybe is not a good idea. So let's guess a different. Let's calculate 40 degrees or something. If that is the thing, then Mn2 will become, uh, if I guess 40, so 40 minus 15 is what? 25. Uh, yes. So Mn2, 25. Well, not 40 then. Let's calculate 35. If 35 is there, then this will becomes 20. So this becomes 0.88. 0.889, let's say. So now if this is the thing, so now we have to use 0.89. So 0.89 corresponds to a value of 1.12. So 1.1289. 3. What will be the Mn M1? So C. Now we'll calculate Mn M1. If I have to calculate Mn1 M1, so this will become here. You will have Mn1. These values will change. So beta is 30 here, and this value is 1.1585. So this becomes 3.17. Okay. And if it's other way around, if it's 1.1289, 1.129, and then beta is 35, so you get 1.96. 1.968. 1.968. Now for this Mach number and theta value we have, theta value is 15. Let's see if we can get some new beta values. So now we will recalculate beta. Okay. So if we do that, so now Mach 1 is 3.17, and beta value or the theta value we know is 15. So what is the value at this? It's 31.1. Close enough. 31.1. And what is the value at 35? At 35. So this one is 1.96, huh? 1.96. 1.968. So this beta value corresponds to 46, which is very far away. So 46. So we know that it is closer to 30, somewhere 30, right? And if we come on now guess next, if we guess 25 degrees, or let's say 29 degrees, let's say 29 degrees, then this value will be, this will be what? So actually, the actual value comes around 29.2. So let me guess that directly. So for 29.2, let's start seeing what results do we get. Okay, if we do that, then we have M can be taken as 2.5935. This angle will be 9.2, so that Mn2 comes out to be 0.414. Okay, corresponding MN1 414 is 5 point. Oh, there's something wrong. Wait. So 29 minus 15 is what? Uh, it's around 14.2, right? It's 14.2. 14.2. It's 0.636. 0.636. 0.636. 1.717. 1.717. This one will be 1 point. So now this is 1.717. This is what? 29.2. So you get this to be 3.51. 3.5152 actually. And now if Mach number is 3.52 and theta is 15, then the value we get is 29.2. So this is a value which converges. This is the value which converges. But now you see because of the so now you see that because of this implicit nature in these theta, beta, and m, you have to sometimes implicitly or guess values and converge to a solution. Sometimes you don't can't find a solution directly. Okay, so that is there. I think we can close at this point. These were the two problems that we discussed. You were able to see the procedure I followed, and yeah, so that's it. So let's close this and let's meet next time. Okay, let me see. Okay, yeah, great. I'll see you next time.